Hello, my name is Gali and I'm a PhD student at the Technion Israel. This paper is a joint work with Professor Maurice Herlihy from Brown University and my advisor, Professor Erez Petrank. In our work, we present VBR, a new manual reclamation method. VBR is lock-free, and in particular, it guarantees a small bound on the number of unreclaimed objects at any given moment. VBR is also highly efficient and does not incur a high overhead when integrated with an existing concurrent implementation. Depending on some standard implementation assumptions, VBR is applicable to a wide set of concurrent data structures. And finally, as opposed to existing manual reclamation schemes, VBR is fully optimistic. It allows threads to access reclaimed memory, both for reads and for writes. Manual reclamation methods rely on retire invocations by the program, announcing that a certain object has been unlinked from the data structure. After an object is retired, the task of the memory reclamation mechanism is to decide when it is safe to reclaim it, making its memory space available for reuse in future allocations. Previous works defined a set of desirable reclamation properties. Safe reclamation algorithms should be fast and applicable to a wide set of concurrent data structures. In addition, reclamation schemes should be robust. A slow executing thread should not prevent the reclamation of an unbounded number of retired objects. Conservative manual reclamation schemes can be roughly classified as either epoch-based, pointer-based, hybrids of these two approaches, or optimistic access. Epoch-based schemes are often fast, but they are not robust. A stalled thread may prevent the reclamation of an unbounded number of retired objects. At a worst-case scenario, these objects will consume too much memory space, resulting in blocking all new allocations and foiling system-wide progress. While pointer-based methods can guarantee robustness, they incur significant time overheads. Using expensive memory synchronization fences for each memory access often results in poor performance. Furthermore, in terms of applicability, pointer-based schemes are not applicable to many concurrent data structures. Hybrids of these two schemes are often performance-oriented. Their robustness and applicability depend on the specific algorithm. Optimistic methods allow threads to access reclaimed memory while taking care to preserve correctness. Optimistic executions guarantee robustness along with high throughput and applicability. However, previous optimistic methods did not go all the way. While reads were executing optimistically, writes were handled with pointer-based approaches. Our version-based reclamation algorithm, VBR, is the first full optimistic solution to lock-free memory reclamation. Moving on to VBR, it clearly satisfies all of the desirable properties. First, VBR allows the immediate reclamation of each retired object, regardless of the behavior of the rest of the executing threads. This obviously yields robustness. In terms of performance, as we show in the evaluation, VBR outperforms other safe memory reclamation methods. It optimistically allows access to reclaimed objects while avoiding expensive memory fences for pointer protection. Finally, thanks to its small set of assumptions regarding the original implementation, VBR is applicable to a wide set of concurrent data structures. Here are some well-known concurrent data structure implementations that can be easily integrated with VBR. In particular, pointer-based reclamation methods are not applicable to the algorithms marked in red. As opposed to most pointer-based methods, VBR is applicable to these algorithms as well. I am now going to give a brief overview of VBR using a linked list example. Similarly to many epoch-based reclamation algorithms, VBR maintains a global epoch counter and tracks the birth epoch and the retire epoch of each allocated node. The birth epoch is determined upon allocation, and the retire epoch is set upon retirement. Upon an allocation of a node, a thread makes sure that the retire epoch of a given reclaimed node is smaller than the current global epoch. If it isn't, the thread increments the global epoch. This ensures that an object is reallocated at a global epoch that is strictly larger than the retire epoch of its previous allocation. Next, the thread reallocates the object by updating its birth epoch with the current global epoch and initializing its retire epoch. We allow optimistic reads in the following manner. Since a node is always reallocated at an epoch that is strictly larger than its former retirement, stale values can be read only upon epoch changes. For example, if the middle node here is deleted, it can be reallocated only after an epoch update. Therefore, VBR allows to optimistically access objects while constantly checking the global epoch. When a thread observes an epoch change, it conservatively assumes that a value was read from a reclaimed memory and applies a rollback mechanism, returning to a predefined checkpoint in its code. Allowing optimistic writes while avoiding the ABA problem is a bit more challenging. In addition to the birth epoch and retire epoch, each mutable field is associated with a version. In this linked list example, it means that the next pointers have versions. When updating a pointer from a certain node to another one, the pointer's version is set to the maximum birth epoch of the two nodes. Consider these two nodes. If the right node is deleted, then its retire epoch must be at least 12. In case it is reallocated, the global epoch must be incremented at least once, and its birth epoch must be at least 13. If the left node points to the new allocated one again, the associated version is 13, and we are ABA safe. For evaluating throughput of VBR, we implemented Michael's lock-free linked list, a hash table based on this implementation, and Herlihy and Sheffie's lock-free skip list. We evaluated VBR against an execution in which memory is never reclaimed. We also evaluated VBR against optimized variants of the original epoch-based and hazard pointers algorithms, and against two hybrids, interval-based reclamation and hazard errors. Each test was a fixed time micro benchmark in which threads randomly call the insert, delete, and search operations according to 3 workload profiles. Each experiment lasted 1 second and was run with a varying number of executing threads. Each experiment was executed 10 times, and the average throughput across all executions was calculated. Here you can see the results of our write-intensive experiment, run on a hash table with a range of 1 million keys. We measured throughput in million operations per second as a function of the number of executing threads. VBR outperforms epoch-based competitors due to its infrequent epoch updates. Most global epoch accesses during VBR hit the cache and are negligible in terms of performance. In addition, VBR outperforms its pointer-based competitors since it does not require memory fences when reading. As shown here, VBR's throughput is around 65% of the no reclamation execution for the write-intensive workload. It outperforms the next best algorithm, EBR, by up to 40%. VBR also outperformed its competitors in other data structures and under different workloads. Other results appear in the full version of our paper. In summary, we propose VBR, a lock-free and fully optimistic safe memory reclamation algorithm. We have demonstrated VBR's high applicability and efficiency against state-of-the-art competitors. Thank you for listening.